All right, so for the first part of today's lesson, I want to do a quick recap about the different types of chemical reactions that we've studied in the last short time, and also predicting the products of those reactions. So before we begin, let's just do a quick overview of the classes of chemical reactions that were covered in class. So the first reaction was the synthesis reaction, and you'll remember that its general formula is A plus B, where A and B are just simple elements, reacting to make a single compound AB. And of course, in order to get the formula for our compound AB, we're going to have to remember the ionic charges for element A and B, and then perform the crossover rule to get our product. All right, so the next reaction was the decomposition reaction. So the decomposition reaction, you'll remember, is the exact opposite of our synthesis reaction, in its simplest form anyway. And so that's where we begin with a compound, AB. And through the reaction, that compound is going to break down, hence the name decomposition, into its elements A and B. And so the only thing we need to be aware of in these types of reactions are whether A or B might be diatomic, in which case then we're going to put the appropriate subscript 2 there. So the next two types of reactions that were covered in class were the single displacement and the double displacement. So in the single displacement reaction, we start with an element all by itself, which I'm going to call A, and we're going to react that with a compound, which I'm going to call B, C. And through the reaction, what we see is we see A bumping out B. So A is maybe going to be able to bump out B out of the situation and then combine with C. And so what we get as a result is A will now be with C, and then B will be left all on its own. Now you'll remember that in the case of a single displacement reaction, we're going to need to look at something called the activity series. And so that's something we're going to need to consult before we make sure what happens in the reaction. All right, secondly, we have our double displacement reaction. And so our double displacement reaction is probably the most complicated of them all. And this is where we start out with a compound AB, and we're going to react it with another compound, which I'm going to call CD. And in this case, what we see is A is going to pair up with D. So in other words, the cation in AB is going to combine with the anion from the second compound. And then we're also going to see the cation C combine with the anion from our first compound B. And so what results is compound AD and compound CB. And so we don't need an activity series in this case, which makes it, in some respects, a little bit easier. And so the final class of reactions that we've seen in class is the combustion reaction. And so the combustion reaction, some students, if they remember about it, to consider it, it's actually pretty easy. So you recognize the combustion reaction because you always have something called a hydrocarbon. And a hydrocarbon is a compound that contains carbon, some number, I'm going to use an X here because I don't know how many carbons would be in the compound, and hydrogen, and I'm going to use the subscript Y. So for example, I might have C2, H5, I might have C8, H18, some number of carbons and some number of hydrogens in a compound. So regardless, the one thing that they all will have in common is that it will all be a reaction with oxygen. And so when I combust something, I'm burning it in oxygen. And what that results with in all combustion reactions, if it's complete combustion, is a carbon dioxide and a water. And so for all of these reactions, the products are simple. It's always going to be that same set of products that I produce. So in our activity today, we're going to look at some specific examples. I'm going to ask you to classify the reaction as one of the 5 that we've discussed and then predict the products. And so what I'm going to hope that you do is that you try these problems yourself, try to work them out, and then by pausing the video, and then resume your video when you are ready to analyze how you did on the particular question. And if you need to listen to the first example in full to kind of get a handle on it, then go ahead and do that. So when I look at this reaction, the first thing I want to do is try to identify what type of reaction it is. And so I do that by looking at what the starting materials are, what my reactants are. And in this case, I see calcium, and it's an element, and I have oxygen, and it's also an element. And so elements and an element combining with another element is an example of a synthesis reaction. So this is clearly a synthesis. So if you're asked to name the type, that's what it is. And so to analyze my products, to figure out what my products are, I'm going to do a little bit of work on the side here before writing down what my response is over here on the product side. And so to do that, I look and see, well, what are the elements that are involved? So when calcium decides to form a compound, it ionizes and it will gain a positive 2 charge. And when oxygen ionizes, it will form an ion with a 2 negative charge. And so then, of course, I take my charges and I cross them down. And a 2 and a 2 will give me Ca2O2. But I need to remember that this is an ionic compound, and ionic compounds I want to be able to reduce to lowest terms, and a 2-to-2 ratio is the same as a 1-to-1 ratio. And so that tells me that my final product is CaO, and then I go ahead and I just write that in my product space here. Now, if I wanted to be extra fancy, I could go ahead and balance this equation, and so you may be asked to do that as well. And so I can see that over here on the reactant side, I have 2 oxygens, and I only have 1 oxygen over on my product side. And so I'm going to put a 2 in front of my calcium oxide. But now I've inadvertently changed the number of calciums that I have, and so I need to go ahead and take care of that by putting a 2 in front of my calcium, and now it is balanced. All right, let's try a next example. So again, pause the video to try the question out. All right, so this question, if you recognize it as it is, then it's pretty simple. So I look at this and I see, well, I have a compound that contains carbon and hydrogen in a particular ratio, and so that makes it a hydrocarbon. And I also see that it's reacting with oxygen. And so quite clearly, if I recognize it, this is a combustion reaction. So hopefully you did okay with that. Combustion, let me spell that properly. And so in that case, my products are simple. My products in a combustion reaction, and we're going to assume it is a complete combustion, are always CO2 and H2O. And again, if I wanted to go ahead and balance this, then I could. In the interest of time, I'm not going to. I'm going to move on with some more examples. All right, so here is our next example, PbCl4 reacting to make a particular product or products. Take a minute to pause the video and try the question out. All right, so when I look at this reaction, I see that I have a single compound reacting. And so when I see that, that is my cue that the only thing that can happen here is for this compound to break apart into its elements. And so if that is the case, which it is, then I simply have a decomposition reaction. So decomp. So hopefully you got that okay. Now let's go about predicting our products here. In a decomposition reaction, I simply want to take the elements that are in that compound and break them up into the respective elements. And so on my product side, I'm going to start by writing out Pb plus Cl. And then I want to take special note of each of these elements, identifying if either of them are diatomic. And so remember that I want to think about Hofbrinkel, to help me remember which elements are going to be diatomic. And I see that, chlorine is diatomic. It's on my list here, and so I'm going to go ahead and add a subscript 2 in order to make sure that that is written appropriately. And if I wanted to, I could go ahead and balance this. I see that I need to add a 2 in front of my chlorine to give me the fluorochlorines that I have on the right-hand side, or on the left-hand side, rather. Okay, so in this next reaction, I want you to pause the video and give it a try. All right, so when I look at this reaction, I can see that it's taking the form of a synthesis reaction. So I have a single element reacting with a compound. And so if this goes as planned, then what will happen is lithium will bump out sodium and then replace it and pair up with bromine. But there's something that I need to be aware of, and hopefully you thought of it as well. So hopefully you remembered to think about the activity series, and so the activity series describes whether a reaction will actually happen or not. So remember, let me just remind us what our reaction is here. I have lithium and I have sodium, and sodium was with bromine, so NaBr. So in order for lithium to be able to bump out sodium, it has to be more powerful than sodium. It has to be higher on the list. So let's check out the relative positions. Lithium is right up here, sodium is below it, so that actually works. That means that this reaction can happen as planned. So now I want to go about the process of predicting what's going to happen here. And so the first step in doing that is going ahead and breaking down all of the elements into their ionic charges. That's really important because we still have to remember the crossover rule here. So lithium as an ion will have a positive 1 charge. Sodium will have a positive 1 charge as well. And I'm getting this again just from our periodic trends on the periodic table. And bromine will have a negative 1 charge. So lithium is going to pair up with bromine. And so I'm going to just perform my crossover rule here. Lithium and bromine, and I mean if you've done this a lot, then you know how this works out. My positive 1 charge will cross down, and my negative 1 charge for bromine will cross down as well. And that results in the formula being LiBr. And so I'm going to write that over here in my product side, LiBr. But then I have my sodium, which is all by itself. And so I just need to put that in all by itself, just as the element sodium, and I'm done. All right, so next example. And so my next example is sodium sulfate and magnesium fluoride reacting. Take a minute to try this question out yourself. All right, so when I look at this reaction, I can see that I have a compound reacting with a compound. And so that makes this a double displacement reaction. So I'm just going to write DD for double displacement. And what that means is that my ions are essentially going to switch places. The positive ion of my one compound is going to move and switch to go with the anion of my second compound, and vice versa. So in order to make sure that I get the formulas written out correctly, though, I need to take a look at my crossover rule. So the first thing I'm going to do is break apart each of the elements in these compounds into their respective ions. So sodium has a +1 charge. Now sulfate, you have access to your polyatomic ion chart, and so when you check your polyatomic ion chart, you'll see that sulfate has the formula SO4 with a 2 negative charge. And then I look at magnesium, and magnesium has a 2+ charge as an ion, and fluorine has a -1 charge as an ion. And so really all I'm doing is I'm saying, all right, well, sodium, you're going to go with fluorine now instead. Positive and negative ions are going to attract each other. And then I'm going to have my magnesium go with my sulfate. And so when I perform that crossover, let me just do this. I'm going to try to find a little bit of room here on the side. When I perform these crossovers, so again, Na+ and F-, that's going to give me NaF. So there's my first product. And then I look at my second product, which is to have Mg, 2+, go with SO4, 2-. And again, I see the 2 and the 2 are going to cancel out. And so the resulting product is going to be Mg. I'm going to write this down here. It's getting crowded. MgSO4, and I'm done. Hopefully you did okay with that. Let's try another 2 examples before we finish off with this. All right, so the next example is Al plus K2SO4, so aluminum reacting with potassium sulfate. Take a minute to give this question a try. All right, so the first thing I noticed when I looked at this reaction, let me write it out again. I had K2SO4 reacting with aluminum. And so I noticed that I have an element and I also have a compound. So that's a single displacement reaction. So that's what brought me to want to take a look at my activity series to make sure that this is a reaction that can actually happen. So let's find those 2 elements. So potassium is way up here and aluminum is kind of middle of the road. And so what that tells me is that aluminum is in fact not powerful enough, not strong enough to bump out potassium. So potassium is going to be able to stand its ground and stay locked with my potassium sulfate, with the sulfate ion. And so what does that mean for this reaction? It means there is no reaction at all. Hopefully you did okay with that. Let's try our last example. All right, last example of the bunch. Take a look at this, give it a try on your own, pause the video, and come back when you're ready. All right, so when I look at this reaction, again, I'm seeing compound and compound. So whenever I see a compound with another compound at this stage, that's going to tell me that I have a double displacement reaction. So I'm going to write that as DD. And so let's break this down. The first thing I want to do is write out all of my ions in question. So Mg it has a 2+ charge in this compound, and carbonate has a 2- charge, and that's something that you can look up on your polyatomic ion chart to see. Silver, when I look at the periodic table, I can see that it has a +1 charge, and that nitrate has a -1 charge. And so really we just have these compounds switching places. My magnesium is going to want to go with the nitrate in my silver nitrate, and silver is going to want to go with my carbonate. So that's exactly what I'm going to do. I'm going to cross these guys over together. I'm going to cross these guys over together. And when I do that, let me take a look at this on the side over here. So I would have Mg, 2+, and NO3-, put brackets around my polyatomic ion and cross those charges down. I get Mg bracket NO3 bracket 2. So I'm going to go ahead and write that up here as one of my products. Let's see if I can fit that in. Mg bracket NO3 bracket 2. It's one of my products. And then let me look at my other product. And so I'm running out of room here. Let me see what I can do. I think what I'll do is I'll squish this a bit. Here we go. And so I see that I have Ag with its +1 charge, and I have carbonate, which is with its CO3 2- charge, brackets around my polyatomic ion just in case. And when I cross these charges down, then the resulting formula is Ag2 bracket CO3 bracket. And we've talked in class about how if there's no value outside of the brackets here, once I knew my crossover rule with the polyatomic ions, then the bracket doesn't really need to be there. And so given that, let me write my final product here. Oopsies. That would be Ag 2CO3, and I'm done. So if you have any questions, make sure to come in at lunchtime tomorrow in order to practice before your quiz tomorrow, and I'll be happy to help you out.